Today, the Event Horizon Telescope is releasing the first ever picture of the black hole that sits at the heart of the Milky Way galaxy. Now, this is extremely exciting for us because for decades we've been seeing stars, and as the stars come close to Sgr A star, they'll be moving quickly and then they get whipped in a different direction by this unseen object. But for the first time now, we've been able to zoom in right on where that unseen object is and see this bright ring of light that surrounds a shadow that's being cast. Black holes are some of the brightest objects in the universe, and that's because material that's flowing onto them takes all of that energy, all the gravitational energy, and it converts it into light. So black holes actually are some of the brightest objects in the universe. The reason it's so hard to take a picture of a black hole is because they're incredibly small. So for context, if we took the entire Earth and we compressed it down small enough to be a black hole, it would be about an inch across, so you could hold it on your finger. The black holes at the center of the Milky Way are much bigger. They're millions of times as much mass as the Sun, but they're still incredibly small on the sky. It's about the same angular size as an atom held at arm's length. So the first image of a black hole that the EHT produced was the black hole in the M87 galaxy. This is a giant elliptical galaxy with one of the biggest black holes that we know in the universe. It has 6 billion times as much mass as the Sun. Now, our own galaxy has a very different type of black hole. It's actually only about 4 million times the mass of the Sun, so it's more than 1,000 times smaller than M87. So it's a small black hole, and that means that it evolves very quickly. So a day in the life of M87 is a minute in the life of Sgr A star. Things are swirling around, and we can see it changing in real time. We see it flaring and erupting on timescales of days.
For the Sgr A star results, was a big issue in the analysis was that the object itself is not very stationary, right? It's sort of we use words variable and dynamic a lot to describe the appearance of this object. It's not standing still. It's not like taking a picture of a landscape that isn't really changing, right? It's more like taking a picture of a waterfall or something that's really going with time. And we're trying to figure out how to take our tools, which are really intended to take snapshots, right? Intended to take still photos of an object that's not really moving, right? Without a lot of change over the course of the photo's duration, and adapt them to this object that really is varying quite a bit throughout the course of the photo itself, right? So it's sort of like, teaching our algorithms to do a long exposure when they're really only intended to do a snapshot. You have two objects that are vastly different sizes. One is way bigger than the other, but the material orbiting them is moving at the same speed. And so, you can sort of intuitively understand that the material is going to take a lot longer to go around the big object than the small object, because there's just more distance to cover at the same speed. And so that means that what we see, which is the emission from this material that's moving, that material around M87 appears to be moving extremely slowly compared to the size of the system, right? Compared to the size of M87, and compared in contrast with Sgr A star, where the material seems to be moving very rapidly. And slowly and rapidly, this is what we mean by variability, by dynamics, over the course of multiple hours, even over the course of multiple days. And so we can really stare at M87 for a full night with our telescopes. And it just sort of sits there, and it's a still image, and we can just take our data and make an image from that. We stare at Sgr A star for a full night, and that thing, it's orbited many, many times, and the material has come in, and it's lit up, and it's accreted onto it. All kinds of stuff has happened in that time scale. We're not just seeing a single image. When we basically take our data and try to produce a single image from that, it's sort of there's a lot of motion blur in the image. It's a really smeared out version, right? It's like a long exposure. Again, it's like this. It's like you exposed a long time on a waterfall. You get the streaking water rather than the frozen droplets at any given time.
The CFA has been central to the success of the EHT going back many decades. So at the CFA, they developed atomic clocks. And these are used in the EHT to get perfect synchronization from all these telescopes around the world. More recently, the CFA has been involved in developing the technique that lets us take a whole bunch of telescopes and have them work together as a single entity and create an Earth-sized telescope. And then over the past decade or so, dozens of EHT members have been involved in every element of the EHT, from deploying new hardware to sites to allow them to record these incredible amounts of data, petabytes of data, to analyzing those data and turning them into pictures, and then to simulating what a black hole should look like on supercomputers so that we can interpret these images and understand what it means for the space-time near a black hole.
But one of the sort of most fundamental things I think we've learned is well, first of all, this is the first direct visual evidence that there is a supermassive black hole just sitting there at the heart of our own Milky Way galaxy, right? It's the first time we're seeing that. There's been, decades now worth of research and effort in understanding the nature of the object at the center of the galaxy, right? So that is really where I think there's just this wonderful confluence of prediction and observation of this. We thought it was a black hole. There's been measurements of how big it ought to be based on the orbits of stars knowing its mass, and then of course Einstein's theory of gravity, general relativity, telling us if there was a black hole of this mass, this is about how it would look. And then we go and stare at it with this telescope and we see this ring of light. It's just exactly the right size given what these measurements on much larger scales would have predicted. So I think this is maybe the nicest thing that we captured this agreement here with the prior predictions that they simply had no way to access before now.